Okay guys, I thought we'd have a little bit of fun using Mathematica on that charged rod example. And again, you could do this integral, and in fact it might be faster if you're not really good at Mathematica, looking it up in an integral table. I put a new integral table under the top module on the classroom. Let me remember what that module is called. Under crib sheets, which is one for physics, so it has a lot of these more complicated integrals. In order to look this integral up in a table, you do have to do a change of variables. So you have to let u, or some new variable, equal z minus z prime. Okay, but if you figure out Mathematica, you can actually have some fun with them relatively quickly. So I took out all the constants in this problem just to make it easier to type into Mathematica. So I simplified the integral just to look like 1 over the square root of x squared plus z minus z prime squared, remembering that we're doing the integral over z prime. Okay, a lot of people like to type in their formulas into Mathematica like this. I'm a coder, so I like to do it the coding style. So I typed in this particular formula in here into my integrate thing. Z prime is zp. That's what we're taking the integral over. These are the limits. Okay, and I did a bunch of assumptions here, and I'll run it and then I will show you what happens when you don't make those assumptions. So it does take a second. All right, this is what you get. Pretty complicated. Really glad I didn't have to do that by hand. So I'm going to take out one of these assumptions and I'm going to run it again. And the reason why I'm doing this is just so I can show you guys why, or what happens when you don't make all the assumptions. So I'm going to run it again. Running. Mathematica, like any computing program, it doesn't really know what you want. It only knows, right, what you tell it. So here, actually, if I get something called a conditional expression, that basically is telling me I need to put some assumptions into my integral because it's saying this would be the expression, which is the same thing I got before, by the way, but it's assuming that this two straight slashes, that's an or, logical or. So it says x must not be equal to 0, or these two things, L is less than Z and Z is greater than 0, or Z is less than 0, L plus Z is less than 0. So based on this, I could be like, let's assume maybe it has a problem right on the x-axis here. So let's assume that x is not equal to 0. In fact, I probably don't even need this assumption here. We can try it. Okay, and if you don't know all what I just typed out there, you can always find it in the writing assistant toolbar. Some of these things, or you can Google what is not equal to in Mathematica. Okay, and let's run it again, see how that works. All right, so it still wanted L is greater than 0. There's a reason why I did that. Okay, and that's an obvious one if you think about it. It wouldn't make any sense if this rod did not have L greater than 0. That would be weird for a rod. Okay, these other ones, again, I put in there. This one just says that all of these variables are real. They're not complex. So I knew to put that in there because I got a conditional expression with a bunch of reals and complex assumptions. This simplify just makes the output a little simpler, simplifies it algebraically. So we can try running it without that, see what we get. Okay, let's play with this a little bit more. So if you guys notice down here, we can really cheat. And Mathematica is giving us some things that we might want to do with this particular outcome. Okay, so one of the things I might want to do is just plot it. And Mathematica is smart enough to know that I could make a two-dimensional plot in X and Z space. So I could do a 3D plot. But what I wanted, well, I'll show you what that looks like. That's what the 3D plot looks like. Okay, I'm going to change it a little bit. This is manipulate. Actually, you can change the L to have different values and it will recalculate it. The way that it has it, it actually doesn't make sense at all to have L be negative. So I'm going to change, right, because that's the length of our rod. I'm going to change it so it's going from L is 0 to 10. Doesn't, well, let's make it even better. How about 1? Because if it's 0, that's not very interesting. Okay, so now it takes a little bit of time when you move this for it to recalculate. But that's kind of cool. So this is what the potential looks like in terms of a height when we've got a long rod. Okay, and again, we could think about the electric field being the slope of the potential. So the electric field should be pretty strong, close to our rod, and point away from it here. And then it's going to get a little bit different at the edges. And of course, the rod's a little bit shorter. It's going to look even more complicated near the edges. So that's kind of fun. Let's make a different kind of plot as well. Let's do the contour plot. Okay, and again, I'm going to make that same change that I made before. Make L go from 1 to 10, and now I can slide this, and it's just a different way to visualize the field. Okay, now instead of having a three-dimensional plot, the colors are representing the strength of the potential as I move away from the rod. Okay, I can do more fun stuff. Here, here's some options. You can simplify, take derivatives. I'm going to click on more here because actually I want to take the gradient. And if I click on that, I get some crazy thing here. Okay, so the gradient, which is, this is the gradient of the potential, so it is the negative of the electric field. You get some wacky thing here. I'm just going to call that answer for now. I'm going to get rid of the output. And then I'm going to say E field is equal to, actually maybe call this E is equal to negative add B. Okay, now I'm going to run that. And I can do something fun. I'm going to make a vector plot of that. So E field, but I have to tell it what L is. So I'm going to use slash dot notation, which is basically saying for all the places that L is, I want you to replace it with a number. So let's use 10. Okay, and then I have to give it a range. I'm going to use the same range as I have down here. All right, cool. And now I can see the electric field vectors with this vector plot away from the rod, assuming the rod has a length of 10. I can make the rod longer, makes it even cleaner. Rod is right down the center here. Okay, or if I make the rod short, it's looking more and more like a point charge. Okay, so that's kind of fun. Mathematica is fun to play with. I'll upload this so you can check it out too if you are interested.